In the earlier classes we have seen in detail the process of steam methane reforming, and also we have seen the method of partial oxidation. In today's class we will learn about the autothermal reforming method, which is the third method for hydrogen production from hydrocarbons. Now this autothermal reforming, it is a mix of both the processes we have learned, steam reforming as well as partial oxidation, and it carries the advantages of both. Like steam methane reforming, it has higher hydrogen to carbon monoxide ratio, but it was endothermic. So that was a disadvantage, that it required large amount of fuel for providing the heat of the reaction. Partial oxidation, which was an exothermic reaction, so as such no externally heated fuel, no external heating was required, but the process had lower H2/CO ratio. So the advantage of partial oxidation, that it was an exothermic process, is being carried in autothermal reforming. At the same time, the higher H2/CO ratio, which is an advantage of SMR, is also being carried in the autothermal reforming. Now if we see the oxidant which is used is oxygen or air along with steam. So if it is any of the hydrocarbon, then the hydrocarbon undergoes partial oxidation, as well as there is a steam oxidant, so that it gets converted into carbon monoxide and hydrogen. Now the process being, either it can be a thermoneutral process, wherein the entire heat of reaction which is required for the endothermic reaction is met by the exothermic reaction heat produced, or it can be either slightly exothermic. Now slightly exothermic, because it can also take care of the exothermic reactions which are going on in the autothermal reformer, can also take care of the losses which are occurring in the reformer. At the same time, it has a higher hydrogen to carbon monoxide ratio as compared to the partial oxidation, and the heat which is required can be supplied internally rather than externally, which was in the case of steam reforming reaction. The product gas that we will get after an autothermal reformer, however, it will depend on several things, like what are the temperature, exit temperature and pressure, what is the thermodynamic equilibrium composition of the various constituents, what is the composition as well as flow of the reactants, the feed as well as the oxidant, the ratios involved of the oxygen and steam which are used in the reactor. Now if we quickly have a look at the thermodynamic equilibrium, thermodynamic compositions, then we can see that the compositions may vary based on the temperatures. Roughly making that scale here. So this is say temperature in degree centigrade, and we can have like the moles. Now this is roughly around that 750 degree centigrade, that the amount of hydrogen we get is, it rises and it goes to about 2.5 moles. The amount of water, steam, it is being used in the process, as such this goes down, forming the desired products. The methane is being consumed, which is the reactant here, it is being consumed in the process. So roughly these are the equilibrium composition, how does these vary. So hydrogen, this is how the steam is being consumed, methane reactant being consumed in the process, and carbon monoxide is being formed. So, all these depends upon what is the temperature inside the reactor, what is the pressure inside the reactor. So, this is CO which is being formed in the process. Now, autothermal reformer, actually this is a reactor which has to sustain very high temperatures and pressures, because partial oxidation as well as reforming, both the processes are occurring in the same reactor. Autothermal reformer, there are 3 regions to mention. Region 1, which is the combustion zone, then there is a thermal zone, and then followed by a catalytic zone. The fed oxygen as well as natural gas and steam, they are fed into the burner region, and this is the key component of the autothermal reformer, and it serves several purposes. So, the burner, it provides proper mixing of the reactants and oxidant. It also provides uniform temperature. So, it results into uniformity in the temperature across the region. It also, if it is uniform mixing, then it will reduce the soot formation. And a proper burner design is very important in autothermal reformer. It should be such that there should not be any backflow or backfiring of the from the core of the flame towards the burner side. Neither the combustion gases should flow back towards the burner so as to cause burner damage. So, a properly designed burner can ensure safe operations, at the same time can increase the life of the burner. Now, this is the burner region wherein we have a flame, then the combustion reaction, that is the partial combustion of methane, if it is methane as the feedstock, or if it is any of the other higher hydrocarbon, then its partial oxidation occurs. So, methane reacting with half O2 giving syngas, and higher hydrocarbons again undergoing partial oxidation to produce syngas in the process. Other than that, in the combustion zone there may be other reactions that can occur, and in that process we can see hydrogen is being consumed. So, hydrogen here reacts to form water, at this temperature it will be steam. Also, carbon monoxide can also undergo oxidation to produce carbon dioxide in the process, and all these reactions occur in the combustion zone. This has a, so the burner has a flame, turbulent diffusion flame, and that flame, the core of that temperatures are very high. It is higher than even 2000 degree centigrade, temperature could be even greater than 2000 degree centigrade. Now, after this combustion region, the required heat in the thermal region, there are other reactions that occur, and these reactions are either these are water gas shift reaction combined with steam methane reforming, and if these are higher hydrocarbons, then the pyrolysis reactions can also occur of the higher hydrocarbons. React in the thermal zone. So, these are in the thermal zone, various gas phase homogeneous reactions occur, including steam methane reforming, water gas shift, as well as various hydrocarbons, they undergo several reactions in the thermal zone. That is followed by a catalytic zone, wherein again the steam methane reforming as well as water gas shift reactions takes place. These are heterogeneous reactions that occur in the catalytic zone, and water gas shift, these are heterogeneous reactions occurring in the catalytic zone. Now, things to be noted here are, at the top of the autothermal reformer, the temperature which is experienced by the catalytic bed. So, this is the catalytic zone in the catalytic, this is the catalytic bed. So, the temperature in this region which is experienced by the catalyst is very high, 1200 to 1400 degree centigrade, because that is following the thermal zone, which is an integral part of the combustion zone. Now, at these temperatures, the catalyst which is used has to be highly stable enough. So, it should be thermally and mechanical stable to be integrated in that particular temperature range. However, as we go down across the bed, the temperature will decrease, because in the catalytic bed the steam methane reforming reaction will occur, which is an endothermic reaction. And towards the end the temperature of the syngas will be lower. So, it could be somewhere between 700 to 1050 degrees centigrade. So, in the catalyst bed top temperature is higher, towards the end of the catalyst bed the temperature is lower. So, a high temperature gradient is experienced by the catalyst bed. At the same time we can see, since there is a combustion reaction occurring in the combustion zone, the amount of carbon monoxide content in the autothermal reformer will be higher than the steam methane reformer. At the same time, since CO content is higher, so H2 by CO ratio will be lower in case of autothermal reformer. If CO content is higher, that means there is a requirement of high shift water gas shift activity. But at the same time what we observe is, we know that the water gas shift is an exothermic reaction and it is favored at a lower temperature. But the temperature inside the autothermal reformer is higher, as such the water gas shift reaction is less favorable in the ATR reformer. That means the outlet gas syngas will have less amount of carbon dioxide as compared to that would have been from the SMR reformer. At the same time the temperatures involved are higher, therefore the reactions which are taking place in the reformer are fast. The kinetics of the reactions are faster. As such, if autothermal reformer can have a faster startup, can be faster in case of ATR. So, the entire reformer, since it has to sustain under very high temperature pressure conditions, this is made up of refractory brick lined reactor. Now, let us look at the complete process of autothermal reformation. Natural gas passes through the desulfurization unit so as to undergo so that the sulfur containing impurities can be removed from the natural gas. Natural gas is then preheated, with steam it enters into the autothermal reformer and oxygen. So, the natural gas, steam and oxygen enters into the autothermal reformer. Now, it can be either oxygen or it can be air. So, if oxygen is used in the autothermal reformer, that means air separation unit will be required for separating oxygen from the air. However, if air is directly used as an oxidant, in that case the output stream of gas will be diluted with nitrogen. This gas can be, depending upon what is the N2 by H2 ratio, this gas can be used for ammonia synthesis. After it passes through the autothermal reformer, the reactions that we have earlier seen occurs inside the autothermal reformer. The syngas which is obtained after the ATR reformer has to undergo cooling, syngas cooling, because the temperature here can be as high as 1050 degrees centigrade. This has to be cooled down to the temperature which is required for water gas shift. So, roughly 340 to 360 degrees centigrade. It has to undergo water gas shift reaction and followed by the purification step. So as to get hydrogen and carbon dioxide separately. The important things here are that the ratio of steam to methane or oxygen air to methane can be adjusted in such a way that the process can be made thermoneutral or slightly exothermic. Oxygen, where in the beginning it will be an exothermic reaction, in the catalyst bed there will be endothermic reactions that will occur. So, the overall process can be made thermoneutral by appropriate choice of O2 by CH4, oxygen to methane ratio or steam to methane ratio. The product gas composition as mentioned will be dependent on temperature, pressure, the conversion and selectivity of the process, and the typical steam to carbon ratio or oxygen to carbon ratio which are used in the autothermal reformer are steam to carbon ratio of 1 to 2 and oxygen to carbon ratio of 0.5 to 1 in the process. Now, since the process has more of CO2, there are combustion products, and the conversion and selectivity can also be selectively preferred towards the desired H2 by CO ratio using the appropriate catalyst support and promoters. Catalyst we have seen earlier, the requirements for these catalysts are that they should be thermally and mechanically stable, they should provide higher conversion and selectivity, they should be less prone to sintering and deactivation, should have low cost, long cycle life. All these are requirements from the catalyst. The most widely used one is again same as was used in case of steam methane reforming, nickel on alumina support. This is used because it is cost effective, it is stable and it has good activity. Other than nickel, the other transition metal catalyst could also be used, copper, cobalt, iron, they have also been used as a catalyst. Non-noble, non-transition metal, the noble metal catalyst, they have a better conversion, they have a better selectivity, at the same time they are less prone to sintering as well as deactivation. But the cost is the major challenge while using noble metal. As such, the two can be combined to form a bimetallic catalyst, wherein a certain amount of non-transition metal elements like the noble metals can be used along with the transition metal elements. So, all the three purposes can be met at the same time, getting a better selectivity, conversion of the reactants, having a better stability towards deactivation and coking, and the most important, having a good activity. So, combining both a small amount of noble metal catalyst with a non-noble metal catalyst can be used. Other than the transition metal and noble metal catalyst, perovskites are also being used as catalyst. There are various supports that can be used like magnesium oxide, cerium oxide, zirconium oxide, and these can be mixed together. So, like alumina and zirconia, when they are used, in that case they have a better stability as well as better conversion. Zirconia, that provides good conversion, they provide a little basicity of the support also, so reduces coke formation. Ceria, that provides a higher thermal stability. So, that way these can become there can be mixed of these oxides so as to act as a support, and support serves various purpose here, like it can stabilize the catalyst, it can provide the required surface area, it can provide the dispersion of the catalyst, it could reduce the coking and sintering by having an interaction with the catalyst, it could provide the required basicity. So, there are several purposes that support can do here. A small quantity of promoter can also be added, and that reduces the coke deposition, like the calcium aluminate or potassium oxide. And these numbers that we have, the parameters that we have mentioned here, like selectivity, conversion, can be defined as the number of moles, for example for methane conversion, number of moles of methane which was in the reactant side, minus the amount of methane which was unreacted to the amount of methane in the feedstock. Same way we can define the yield, the amount of hydrogen we have got as against the amount of reactant feedstock, and selectivity of the desired product as against the other undesired products. To summarize this particular ATR section, let us see that what are the differences of this as against the other two processes. Autothermal reformer, like the partial oxidation, requires oxygen if it is to be used for applications wherein pure hydrogen is required, or where it is that methanol synthesis process where the oxygen is used and we do not want the outlet stream to be diluted with nitrogen. At the same time, the requirement of oxygen in partial oxidation is higher as against the autothermal reforming process, and similarly for autothermal reforming the requirement of steam is lower than the steam methane reforming process. Again the ATR process, herein the chemical kinetics as well as both the heat and mass transfer, they are the major limiting factors deciding the overall process. Compared to steam methane reforming, since there are no external heat exchange required, like the energy or heat which is required for the reaction is provided within the reactor, as such the startup time which is required is much shorter compared to the steam methane reforming process. It has a better efficiency compared to the partial oxidation, because the energy or heat which is produced in the exothermic reaction is being used in the endothermic reaction. So, the thermal efficiencies are comparatively better than the partial oxidation. The design of the autothermal reformer is comparatively simpler. There are different ranges in which we can produce H2 by CO, there are various wide flow ranges which are possible. At the same time, since we are using steam, the possibility of hotspot formation inside the reformer is reduced. The temperatures which are encountered in the autothermal reformer are lower than the partial oxidation, and as such the problem of sintering is lowered in autothermal reforming process. And we can use other fuels also, can get high purity hydrogen. The coke which is formed can be burned off during the catalytic regeneration. Now let us compare all the three processes that we have learned so far. The steam methane reforming process, partial oxidation and autothermal reforming based on several parameters. If we consider the thermodynamics of the process, then steam methane reforming was an endothermic process that we have seen, partial oxidation exothermic process, autothermal reforming is either a thermoneutral or it can be made slightly exothermic so as to encompass the losses also that are occurring in the reactor. In terms of heating requirement, in SMR the reformer which are filled with catalyst tubes, they are externally heated, and in partial oxidation there is no such indirect heating involved. The heat of the reaction which is required for the endothermic reaction is being generated within the reactor itself, and same is for autothermal reforming. The thermal efficiency with the use of several heat exchangers is higher in case of steam methane reforming, but in partial oxidation there are exothermic reactions occurring and it is very difficult to recover the excess heat which is obtained in the process. So, the degree of heat integration among the various processes is not like it was in case of steam methane reforming. In autothermal reforming, comparatively the system efficiency is higher than partial oxidation because the heat produced is utilized by the reaction within the reactor, but at the same time the reaction heat cannot be completely recovered. So, the excess heat which is being produced cannot be recovered in the process. If we compare in terms of hydrogen to CO ratio, it is highest in case of SMR, it can go 3 to 5, in partial oxidation 2, in fact less than 2, and for ATR this can vary depending upon the steam to feedstock ratio, steam to carbon ratio or steam to oxygen to carbon ratio. So, this can be 2 to 2.5 or it can be more, wide range we can get. Compared to partial oxidation this is higher, but compared to steam methane reforming this is lower. Now this method of steam methane reforming is preferred in case where we require hydrogen rich syngas, or the processes where we want pure hydrogen, we can separate out the other impurities from the hydrogen in the purification steps and then we can get pure hydrogen, or in processes where the H2 by CO ratio required is higher, there we can use the syngas. In partial oxidation, since the H2 by CO ratio is lower, this would be preferred for processes where this is ideal ratio for methanols production or for other liquid fuels production. In ATR this ratio can varied, it can be changed and it can be adjusted as per the desired application. If we see the reactor size and complexity, since herein there is heat transfer, reactor performance is limited by heat transfer and reactor is designed so as to have heat exchange. So, these reactors are usually bulky and heavy. However, they are suited for long periods of steady state operation. For partial oxidation the reactor size is small, there is no external heating requirement in the process and there are no bulky heat exchangers. So, these are much more compact in size, but at the same time these are complicated because there are several reactions which are exothermic, highly exothermic. So, it has to be operated within the explosive limit, that we need to be careful. ATR, it is reactor is comparatively smaller than the steam methane reforming, but it is bigger than the partial oxidation. There are no external heat sources or heat exchangers, indirect heat exchangers, and that makes them simpler and compact than the steam reformer, and that results in a lower cost. So, these are simpler as well as these are compact. If we compare on the basis of the response time, since the process in SMR is of high endothermicity, so the reactor is externally heated, so it requires a long time for starting it up or shutting it down. So, the response time, these are not meant for dynamic operations, very faster operations. Short startup time is observed in case of partial oxidation as well as autothermal reforming. In steam methane reforming, superheated steam is required. In partial oxidation, air or oxygen is required. If oxygen is to be used, then air separation unit has to be added, and same is with for autothermal reformer. There is a limitation in steam methane reforming, that is heat and mass transfer limitations as well as the chemical kinetics based limitations. In partial oxidation these limitations are comparatively less if it is non-catalytic partial oxidation. If it is catalytic partial oxidation, then since the temperatures are high in case of partial oxidation, there could be hot spots, non-uniform temperature distributions inside, catalyst could get sintered because of that high operational temperatures. This can be controlled with the use of steam in case of autothermal reformer. Overall system, it is large for steam methane reforming, compact for partial oxidation but it is complicated, and simple and compact for autothermal reforming. There are several catalyst related challenges like carbon deposition in case of steam methane reforming, but these are comparatively much less than the other two processes, because the reactions which produce carbon, they either dominate at the very low temperature regime or these are not much favorable in the temperature in which the reformer operates. Non-catalytic partial oxidation, there is no catalyst deactivation problem, but in catalytic partial oxidation both the problems related to deactivation and sintering are there, and non-uniform heating and mass flow rate can lead to even catalyst sintering, breakage and consumption. In autothermal reforming, the problems challenges are sort of intermediate. Deactivation and sintering is there, but due to presence of steam that deactivation can be reduced and sintering is lower than the partial oxidation. So, the temperatures and pressures like 700 to 900 degree, 15 to 30 bar for steam methane reforming. For partial oxidation 1000 to 1400 degree centigrade, 30 to 80 bar pressure. For autothermal reforming 800 to 1300 degree centigrade, 20 to 80 bar. Thermal management, it is required in case of steam methane reforming, and the materials, the reformer tube, special tube materials is required, and there are metallurgical challenges. Steam can also corrode, they have to bear the high temperatures and pressure. However, here in both the processes refractory brick lined furnaces are being used. Fuel consumption, it is high in steam methane reforming, response time is higher, startup is complicated. However, the amount of fuel which is required for providing the appropriate reaction conditions is lower in case of partial oxidation and autothermal reforming. So, comparing everything, we can see that the efficiency is highest in steam methane reforming, it is lowest in partial oxidation and intermediate between partial oxidation and steam methane reforming in the autothermal reformer. So, we have seen all the 3 processes which are used for hydrogen production from the hydrocarbons, and we have compared each of these. Thank you.